This lesson is actually about counting theory. So we are going to start with the fundamental principle of counting. So we're going to take a look at this example, right? We've got 3 roads from Albany to Baker and 2 roads from Baker to Crestwich. And we want to know how many ways can you travel from Albany to Crestwich by way of Baker. So what they did is they created this, which is called a tree diagram. We start in Albany, and we can take either one of these roads to Baker. And then outside of Baker, we've got 2 roads to Crestwich. And this is called counting theory because we count how many options do I have. Okay, well, there's an option. That's 2. There's 3 and 4. There's 5 and 6. So there are 6 ways to get from Albany to Crestwich by way of Baker. Now, hopefully, one thing that you thought about in that last thing was that we had 3 ways to get from Albany to Baker and 2 ways to get from Baker to Crestwich, and we had a total of 6. So what happens is the fundamental principle of counting, which is what you see in this green box. Pretty much what it's saying, if there's this many ways for the first event to occur, first event would be Albany to Baker, and this many ways for the second event to occur. The second event would be Baker to Crestwich. Then essentially all you have to do is multiply all those ways together to find out the different ways for all of those events to occur. So what we'll do is we will put this in action, right? We're looking for a desktop computer system. We've got 6 computers, 4 monitors, and 3 printers. Now we could make a tree diagram with all 6 computers, and then from there, 4 monitors for each one of those 6, and then 3 printers. That's going to take up a lot of space. Instead, what we can do is use the fundamental principle of counting. We've got 6 of the first, 4 of the second, and 3 of the third. So now what we see is that we've got, and I think of it like this, 12 times 6. There are 72 different systems that can be assembled from these choices. So now we'll look at Mrs. Dorfman. She is moving into a retirement community, and she's got 9 different pictures, probably her grandchildren, that she wants to hang in a row on her wall. How many arrangements do we have? When you think of something like this, what I tend to do is draw out a space for each one, right? So we've got, there's my 9. So in the first spot, I have 9 choices. When I get to the second spot, I only have 8 choices. Then I have 7 choices, 6 choices, 5 choices, 4 choices, 3 choices, 2 choices, and 1 choice. And I multiply all of these together. We call this 9 factorial. And you actually can plug this directly into your calculator. When you calculate 9 factorial, what you will find out is there are 362,880 arrangements of 9 pictures. Now suppose that Ethel gets to pick her 6 favorite grandchildren. How many arrangements are then possible? So again, we've got 6 choices, but we have 9 pictures that can go in the first slot. 8, 7, 6, 5, and 4. And we would multiply this. This is something that we call permutations because we're taking 9 elements 6 at a time. If you put this into your calculator, you'll find out that there are 60,480 arrangements of 9 items taken 6 at a time. Notation for permutations is shown here. Now remember we had that factorial, but in order to get rid of those pieces that we don't need, we actually divide it. So what that looks like is, say for the above, we had 9 factorial, right? But we couldn't go all the way to 1, right? How about I do that correctly? 7, 6. So what we do is we divide this by those pieces that we don't need, which would be 3 times 2 times 1. So really what we've done is we've said 9 factorial divided by 9 minus 6 factorial, and that leaves us with exactly what it was that we're looking for. There are calculator steps for this as well. So to use your calculator to find the number of permutations for Miss Ethel Dorfman's issue with the 6 pictures out of 9, what you'll do is, we know that we've got 9 items, so you put in 9. Then on your calculator you go to math, you're going to need to arrow all the way over to probability, and we're looking for permutation, so we went NPR. And we get to choose 6 items. And you hit enter, and there's our answer. She gets 60,480 ways to hang 6 out of 9 pictures on her wall. So let's try a few more examples. The number of permutations of these digits. So what we've got is the probability of 5 items taken 5 at a time. I put that into my calculator and I find there are 120 permutations of this. I can do the same thing, the permutation, the number of permutations of 4 of these digits. So again, I'll write this in a little bit different notation, although it's really the same. I'm going to take the permutation of 5 items taken 4 at a time, and I'll put that into my calculator. And I get 120 again, because if you think about the one above, we had 5 factorial over 5 minus 4 factorial. Well, 5 minus 4 is 1, so that actually goes right there. So that's why you end up with the same value. So then how many ways can they install 10 different billboards in the 10 locations that they have rented? So once again, I'm looking at a permutation. And I will again use a slightly different notation just so that you see it. I've got 10 items that we're taking 10 at a time. And there are 3,628,800 ways that they can install those billboards. Now in the previous examples we were looking at arrangements. We didn't actually look at this particular example 3, but we can arrange 3 of 5 different books in a row in 60 different ways, meaning that there are 60 permutations of 5 things taken 3 at a time. However, let's imagine that now we're not necessarily wanting to arrange the books, but really we're just wanting to select 3 out of the 5 books to donate. Does it matter which book that you donate first? Probably not. So what we do here is we're looking at all these arrangements that would give us that 3-book set, but essentially we end up with the same 3 books regardless of how we arrange them. This is called a combination. Combinations of elements differ from permutations in the fact that combinations, the order doesn't actually matter. Permutations, like arranging pictures on a wall or books on a shelf in a specific order, that matters. Combination, it doesn't matter. We're just selecting any number of items. We again have calculator steps, but this would be the formula to represent this. We might write the notation like this or this way. the steps for combinations are actually pretty similar. So remember, we had the 5 out of 28 employees that we're choosing to go to a conference. So we start with our 28 employees. You go to math. Here's a little trick. If you arrow left, it'll scroll you back over here. And now we want the combination, and we're choosing 5. And there's your answer. So now we've got a college club with 22 members that needs to choose 4 to attend a conference. How many ways can we do that? Well, we're looking for a combination of 22, and we choose 4. So when we put that into the calculator, we get 7,315 different ways. The next problem, we've got 28 employees, and 5 of them get to serve on the committee. How many different ways can we select this committee? Well, again, we would say that we have 28, we choose 5. Plugging that into the calculator, we find that it's 98,280. Now, the next one is a little bit different because there's one person that has to be included. So how many ways can we select 5 of these members if last year's chairperson has to be included on the list? So here what we have to do now is say, rather than 28 employees, we're really looking at 27 employees because that one person got removed. And instead of selecting 5, we're really now selecting 4. So now that we've thought about the problem in a slightly different manner, we can now enter the information into the calculator, and we find that we get 17,550. Distinguishing between combinations and permutations really is the hardest part because most problems aren't going to say, find me a combination of this or a permutation of that. What you're going to be looking at are word problems. So there are some keywords that you need to look at. You're looking for arrangement, for schedule, for order. These are all words that are going to tell you we want a permutation. If you see the words group or committee or sample or selection, those are words that will tell you that we're looking for a combination. The big idea is that on a permutation, the order of those items are important. On a combination, the order is not important. On a permutation, we're looking of arrangements of a set. For a combination, really we're looking at a subset of whatever that group is that we had. So now let's take a look at a few problems, and all we're going to do is decide whether or not it's a combination or a permutation. So the first one, in how many ways can oranges be chosen from a bin containing 20? So the question you ask yourself is, does the order that I select them matter? If the order does matter, it's a permutation. If the order does not matter, it's a combination. So for this one, the order of oranges does not matter. The next one, a website requires each user to select a 5-letter password in which no letter may be repeated. How many passwords are available? So again, if we're looking at passwords, does order matter? In this case, absolutely. This is a permutation. I'm going to leave the last 2 for you guys to do. So there's an illustration in your textbook on page 1049 that shows sort of the distinction between permutations and combinations. And what you're looking at here is selecting 2 cans of soup out of 4 available. So N is for noodle soup, B is for bean soup, M is for mushroom soup, and T is for tomato soup. If the order that you're selecting these 2 cans matters, this is what it looks like. If the order doesn't matter, it looks like this. So let me show you. Here you've got noodle soup, bean soup, noodle soup, mushroom soup, noodle soup, tomato soup. We all pretty much seem to understand why we have that. But if you look at this next branch, we have bean soup, mushroom soup, bean soup, tomato soup. The reason that we're lacking this third branch of the tree, right, which we would have called noodle soup, is because bean soup and noodle soup have already happened here, and because the order that we're selecting doesn't matter, we don't actually need to repeat that selection, which is why when you're looking at combinations, the number of ways things occur is far fewer.